Now, I was pretty harsh on rings in my previous video, but in this one, I will try my best to redeem myself and shine some light on them. More precisely, we're gonna derive the expression for the electric field of a charged ring everywhere in space, not just on the axis that passes through the center of the ring. I was assigned this problem as part of my electrodynamics course, and the knowledge I gained while solving it greatly improved my skills in the field and helped me pass the exams, and I hope it will also improve yours as we go through the entire derivation, because, unlike Balrog, you shall pass electrodynamics. Because the derivation is quite long, doing and explaining everything in a single video is a little overwhelming and it would take a lot of time, so I will split this problem into two videos. The first step is to find the expression not for the electric field itself, but for the electric potential. Solving for the potential is much easier than immediately finding the field because it is a scalar quantity, whereas electric field is a vector quantity. And it's always less of a headache to deal with scalars, as proven by my first video on the double pendulum. Once we have the potential, we find the electric field by taking a negative gradient of it. This first video will only involve solving for the potential and showing that it can be expressed in terms of elliptic integrals.
What are those?
Honestly, for purposes of this video, it is just some special function of a certain form, and I won't go into much detail about it here. I will elaborate more on it in the second video, where I will lay down some basic info about elliptic integrals in general that will be needed as we go further through the derivation. And I will take the gradient of the potential to find the field in the second video as well. Without further ado, let's get to the ring. We have a ring of radius r. A ring that can produce an electric field needs to be electrically charged, so we'll let it have some uniform charge density lambda. Charge density is analogous to mass density. Instead of mass per unit space, it's charge per unit space, depending on the dimensionality of an object. The ring is just a curved line, so charge density is equal to charge per unit length. It is therefore a linear charge density. A single point on this ring has some infinitesimal length dl and contains infinitesimal amount of charge dq, so the linear charge density lambda at that point is equal to dq over dl. As the charge is distributed uniformly, lambda is also equal to the total charge of the ring q over the entire length of the ring, its circumference, which is 2r pi. The total charge is then equal to lambda times 2r pi, and we'll use this somewhere later down the line. As is usually the case, we need a coordinate system in which we're going to solve this thing. Let's place this ring in an xy plane, with the origin at the center of the ring, so we have this nice symmetry. We want to find the electric field of the ring everywhere in space, so we need also the z-axis, the full 3D space. Usually when you encounter this problem, you're asked to find the expression for the electric field only along the z-axis. That is the case so often that you can barely find any information for the field everywhere in space, which is the main motivation of this video, outside of me wanting to throw in a couple more Lord of the Rings references.
The ring is mine!
The expression for the potential of a point charge is 1 over 4 pi epsilon naught times q over r, where q is the point's charge and r is the distance from the charge to some point in which we want to calculate the potential in. Ring is not a point charge, but we can imagine that the ring is made of a lot of points of some infinitesimal charge dq arranged in a circle. Every such infinitesimal charge will produce some infinitesimal electric potential dV, and the total potential of the ring we obtain by integrating over the entire ring. We can rewrite dq as lambda dl, and we end up with the following integral. Before we start solving it, we need to find the expression for the distance r. We'll start by defining the position vector r prime of some infinitesimal charge on the ring, whose coordinates are some x prime y prime, thus r prime is equal to x prime x hat plus y prime y hat. It doesn't have the z component because the ring is placed in the xy plane. We can define the position vector r of some point at which we want to calculate the potential. We want that vector to be as general as possible because we want to calculate the potential everywhere. But we can make our lives just a little easier if we notice that, because of the symmetry of the ring with respect to the z-axis, the potential is going to be symmetrical around the axis as well. It's going to have an axial symmetry. So we can place this vector r either on the xz plane or yz plane without loss of generality. Let's place it on xz plane. So r is equal to xx hat plus z hat. Since ring is a curved line, a circle, we again part ways with the Cartesian coordinates and introduce non-Cartesian ones. In previous videos, I used and explained polar and spherical coordinates, and in this video, we're gonna use cylindrical coordinates, which are just the extension of regular 2D polar coordinates. The three cylindrical coordinates are distance from the z-axis, or radial distance rho, the angle which the projection of the position vector of some point closes with the positive side of x-axis phi, and we actually keep the z-coordinate from the Cartesian system. They are called cylindrical because they are the easiest way to express a position of something on a cylinder. We see that x is equal to radial distance rho, while z is still z, so r is equal to rho x hat plus z hat. We're going to use the Cartesian unit vector still, because the cylindrical unit vectors depend on the position of some point, as I have explained in the video with the spring pendulum, while Cartesian ones are constant, therefore easier to work with. We use trigonometry again and find that r prime is equal to r cosine phi prime x hat plus r sine phi prime y hat. Next, we introduce the vector that connects the charge element to the point of interest. The value of that vector is equal to the difference between r and r prime, and the distance between these 2 points, the r from the potential expression, is equal to the magnitude of that vector. The magnitude of a vector is equal to the square root of the sum of its components squared, and we get the following for r. And now we're ready to attack the integral. Plugging everything in, we arrive at the following expression. This line element dl is equal to the infinitesimal arc length of the ring. Its value is the radius r times the angle between the lines connecting the center of the ring to the endpoints of an arc, which is some infinitesimal angle d phi prime. So dl is equal to r d phi prime. The limits of integration are full range of phi, as we are integrating over the entire circle, the entire ring, so from 0 to 2 pi. Now we can solve it, right? Well, not quite. This integral has no analytic solution.
I'll go now.
Fortunately, this integral can be transformed into much more useful, complete elliptic integral of the first kind. As I said before, for purpose of this video, it's just a special kind of integral, a special function that has the following form. It is the integral from 0 to pi over 2 of the x over the square root of 1 minus k squared times sine squared of x. This k thing is called the modulus of the elliptic integral, but all you need to know about it for now is that inside the integral there should be some sine squared term multiply by something, and that something you will just name k squared. Let's do a couple of simplifying substitutions first. Let rho squared plus r squared plus z squared be equal to a, and 2 rho r be equal to b. So we have a minus b cosine phi prime under the square root in the denominator. We need sine squared somewhere, and we can get it if we use the half angle formula. Sine squared of phi prime over 2 is equal to 1 minus cosine phi prime all over 2. From there, we can get cosine phi prime is equal to 1 minus 2 sine squared of phi prime over 2. And we can plug that into the integral. Distributing b into parentheses, we now have a minus b plus 2b sine squared of phi prime over 2. We got just a little closer, but we still have half angle as an argument and different limits of integration. We can remedy this by substituting phi prime over 2 with theta plus pi over 2. Why that pi over 2 part?
Let's find out.
D phi prime will be equal to 2 d theta. The limits will change from 0 to 2 pi to minus pi over 2 to pi over 2. Hey, we have pi over 2 as an upper limit. If we just subbed it for theta, we would have gotten pi as an upper limit. But oh no, there's no longer 0 in the lower limit. However, if we plug the substitution into the integral, we can see this sine squared of theta plus pi over 2. Using the fitting trigonometric identity, this is equal to cosine squared of theta. Now this is an even function under the integral, and limits are symmetric, so we can write this integral from minus pi over 2 to pi over 2 as 2 times the integral from 0 to pi over 2. And now we have limits set. But we lost the sine squared term. But don't worry, old fundamental trig identity is here to save the day. When all is said and done, we're left with a plus b minus 2b sine squared of theta. But if we factor out a plus b and put it out of the integral because it is a constant, and conveniently substitute this 2b over a plus b part with k squared, what do you know? We have expressed the electric potential of a charged ring with a complete elliptic integral of the first kind. That is so cool! But now it's time to find the field. Or rather,
It's time to stop!
because we're gonna do that in the next one.